Okay, let's jump right in. We're looking at this really interesting paper today, Why Less is More Sometimes, a theory of data curation. Now, if you're in the foundation model world, you've probably seen this contradiction pop up. For ages, the scaling laws basically told us, pile on the data, more is always better.
Hmm.
But then you get these results, like from Limo and S1, where they use these tiny, really heavily curated data sets and get amazing performance.
Seems backward, right?
It really does seem backward, and that's the core paradox this paper tackles head on. It tries to resolve that tension between the old more is more idea and this newer less is more curation success. And the key insight they offer boils down to one critical factor: the quality of the source that's generating your training data labels.
Right, the generator quality. So they introduced this idea of a phase transition, meaning the best way to pick your data isn't always the same. Exactly. It depends on this quality score they call rho. Is your generator strong, meaning rho is close to 1, almost perfect? If it is strong, the best strategy is actually to focus on the hard cases, the tricky examples. That's what they call keep hard, KH. It's about refining an already good model. That's why Limo worked.
Okay, refinement makes sense, but what if the generator isn't strong? If rho is low?
Well, then the optimal strategy flips. You actually want the easier examples. Keep easy, KE. The model needs that broader exposure to learn the basics first. So the old more is more kind of holds true in that regime.
Where this isn't just hand-waving, they provide actual scaling laws using random matrix theory.
Yeah, exactly. Scaling laws based on data size, dimensionality, and these quality parameters, rho and rho star. It turns curation from, a bit of a dark art into a principled approach. It helps manage efficiency and, crucially, stability.
Let's dig into why this whole curation thing is even necessary. I mean, why not just throw all the data at the model?
Well, the big problem is inefficiency. Standard training just treats every data point as equally valuable. But think about it. If you have, say, 500 billion tokens, are all of them really teaching the model something new? Probably not. A lot of it is likely redundant, some might be noisy, maybe even actively harmful.
Right, especially for these massive foundation models. So this paper sets up a theoretical playground to study this. How do they formalize it?
They use a pretty standard but powerful setup. High-dimensional binary classification. Imagine trying to separate points in a space with tons of dimensions. The model itself is kept simple, a linear classifier, and then they solve it using standard convex optimization, like L2 loss, with some regularization. Nothing too exotic there.
But the analysis is where the heavy machinery comes in. You mentioned random matrix theory.
Yes. Specifically, they work in the proportionate scaling limit. This means both the number of data points, none dollars, and the number of features, dollars, go to infinity together, but their ratio, DRDL, which they call phi, stays constant. This limit is key because it lets them use RMT to get these exact formulas for how the test error behaves. It captures that interplay between model complexity and data volume that's so characteristic of large models.
Okay, so that's the math framework, but who are the main players in this curation story they're telling?
Good question. They define 3 key conceptual roles. First, you have the generator, often written as $. This is the source labeling your training data.
Like a teacher model in distillation, or maybe human annotators.
Exactly. And crucially, this generator might not be perfect. Its labels might be a bit off compared to the true underlying pattern you want to learn, which they call dollars, that misalignment. That's your noise, your label shift.
Okay, so there's the potentially flawed teacher, the ideal, and the ideal truth. Who else?
Then there's the pruning oracle. This is the entity that actually decides which data points to keep and which to toss out. It uses some criteria, maybe how difficult an example looks, or whether the label seems correct.
But the model that's learning doesn't get to see why the oracle made its choice, right? It just sees the final decision. Keep this one, prune that one.
Precisely. The learner only gets the prune data set. The magic happens in the relationship between these 3 vectors: the true target to dollar, the generator dollar, and the oracle $2.
And that relationship is measured by those rho constants you mentioned earlier.
Yes, the most critical one is rho constant itself, the generator quality. It's simply the geometric alignment, think cosine similarity between the generator dollars and the ground truth dollars. If 2 colon dollars of dollars, the generators are perfect. If 4 colon $, it's useless.
And there are others, like
Yeah, Toro measures the oracle's alignment with the truth, and Torge measures the alignment between the generator and the oracle. They matter for the full math, but for the main intuition, that generator quality oracle is really the star of the show. It determines which side of the optimal strategy fence you fall on.
Okay, so we have the generator, the oracle, and the quality metrics. How does the oracle actually do the pruning? What rules does it follow?
They analyze 2 main types of curation rules. The first is called label-agnostic curation. Here, the decision to keep or prune an example depends only on the input features, specifically how they project onto the oracle's direction $2. The label itself isn't directly considered in the rule.
So this is purely about how hard the example seems based on its features.
Pretty much. This gives you the classic difficulty-based rules. Keep hard, KH, means you keep examples that fall close to the decision boundary, the ambiguous ones with a small margin score, say below some threshold alpha.
And keep easy, KE, is the opposite. Keep the ones far from the boundary, the clear-cut cases with a large margin.
Exactly. But then there's the second type, which is more sophisticated and closer to what systems like Limo actually do, label-aware curation.
How does that differ?
It's stricter. An example gets kept only if the oracle thinks its label is correct, and it meets the difficulty criterion, like being hard or easy. You're filtering on both perceived correctness and difficulty.
Okay, that seems much more powerful. You're trying to keep informative examples that also seem to have the right label according to the oracle?
Right. In this whole setup, the RMT math, the actors, the quality scores, the curation rules, it all builds towards their main theoretical result.
Which is theorem 1 or 3 in the paper, giving the exact test error.
Yeah, they derive this formula that tells you the asymptotic test error based on the data size, dimensions, quality rows, and crucially, the effect of any pruning strategy dollars. That strategy's impact gets summarized neatly into just 4 scalar values.
But the big takeaway, the actionable insight for people training models, comes from theorem 2, right? The part about the optimal strategy depending on row.
Absolutely. That's the core message. The best way to prune to minimize that final test error depends entirely on the generator quality, low or dollar. Let's walk through those 2 scenarios again, maybe with a little analogy.
Okay, let's do it. Scenario 1, high row.
Right. Scenario 1, refinement. Your generator is strong, 3 over is close to 1. Think of your model like a student who's already aced the introductory courses. They understand the basics really well.
So giving them more easy problems is just pointless.
Exactly. It's like giving a calculus expert basic algebra drills. They won't learn anything new, and you're wasting their time. To get better, they need the challenging stuff, the edge cases, the complex problems that push their understanding.
Which means the optimal strategy has to be keep hard, KH. You aggressively filter out the easy, redundant stuff and focus the model's learning budget on the examples that offer the most new information.
Precisely. That's the theoretical justification for why methods like Limo, which often distill from a powerful teacher model and focus on hard examples, can be so effective. It's targeted refinement.
Okay, that makes sense. Now the flip side. Scenario 2, foundational learning. This is when Barrow is low.
Yeah, lower rock. Your generator's weak. Maybe it's early in training, maybe the labels are really noisy, or maybe you're tackling a subset of problems where the model is just not good yet.
So our student is now like a beginner,
Yeah.
just starting out.
Right. And what happens if you only give a beginner the super hard final exam type questions?
They'll probably crash and burn, get totally confused, maybe even give up. Their performance might actually get worse.
Exactly. They need to build foundational knowledge first. They need the simpler examples, the core concepts, the basic patterns in the data. That's why in this low-row regime, the optimal strategy flips to keep easy, KE.
You need that broader exposure to build stability and understanding before you can handle the really tough stuff. The old more is more idea holds sway here.
And this connects directly to a huge practical problem, model stability, especially in iterative self-training or distillation loops.
Where the model generates its own data for the next round.
Yes. And often, early on, the model is a weak generator. Its pseudo-labels aren't great. The theory shows that if you blindly apply keep hard in that situation, low effective dollar, you can actually cause the model's performance to diverge model collapse.
But switching to keep easy, or just using more data without aggressive filtering, provides the stability needed to bootstrap the learning process.
Exactly. Strategic curation isn't just about efficiency. It's analytically shown to be crucial for preventing these kinds of training failures.
Okay, the theory sounds compelling, but does it actually hold up when tested? What did the empirical results show?
They did some really nice empirical validation. The first one used synthetic data, setting up this neat 2x2 grid. They varied the amount of data, low laboratory, and the generator quality, low to Larosse or ISIS high search.
And this visualizes the whole landscape.
Yeah, it really does. And what you see is that the classic more data is better rule, where the lowest error happens when you use all the data, PP-1, holds true in 3 out of the 4 boxes.
Which ones?
It holds when data is scarce, low dollar, regardless of generator quality. And it holds when the generator is poor, low dollars, regardless of data size. In those cases, adding more data generally helps.
But the crucial quadrant, the exception.
The bottom left one. When you have abundant data,
Yes.
$1, only in that specific scenario does aggressive pruning, keeping a small fraction dollars of the data, suddenly become the best strategy. That's the less is more regime, quantified.
Wow. So it really isolates the conditions needed for aggressive curation to win.
Yeah, and they didn't stop at synthetic data. They applied this to a real-world task. Large language model mathematical reasoning using the NME benchmark.
Okay, how did the theory play out there?
It was fascinating. First, they looked at average performance across all ME problems. For this general task, the base LM acted as a pretty strong generator, so north of dollars was relatively high.
So the theory predicts keep hard or aggressive curation should work well.
And it did, spectacularly. They found that using just 1,000 carefully curated tokens selected based on the principles achieved 56.7% accuracy.
Wait, 1,000 tokens? How did that compare to just using more raw data?
Get this. The baseline model, trained on 114,000 unsorted open-source math tokens, only got 50.2% accuracy.
That's incredible. Over 100 times less data, but significantly better performance through curation. That really drives home the efficiency point when trialers is high.
Absolutely.
Right.
But here's where it gets even cooler. They then zoomed in on just the hardest problems within AM. Now, relative to this specific difficult slice of the data, the same LLM was effectively a weak generator. Its raw dollar for that task was low.
Okay, theory predicts. Low row means keep easy or just scale with data size.
Exactly. And that's what happened. For those hardest questions, performance just kept improving as they added more tokens, all the way up to 1 million tokens, where they reached 64.9%. No aggressive pruning benefit there. More data was better.
So the optimal strategy isn't fixed for a model. It depends on the task difficulty you're evaluating against, because that changes the effective generator quality for viewers.
It's dynamic. And they showed this crossover effect in computer vision too, using ImageNet.
How did that work?
They looked at models trained with different amounts of initial data. If the starting model was weak, trained on only 160K ImageNet examples, it acted as a weak generator. Improving it further worked better with the keep easy strategy.
But if the starting model was already strong, trained on the full 1.2 million examples,
then it was a strong generator, high rate. And sure enough, the keep hard strategy became superior for further improvement, pushing performance close to what you'd get by training on expensive, human-verified ground truth labels.
And they confirmed the stability aspect too, in iterative training.
Yes, figure 3 in the paper shows it clearly. In self-training loops using pseudo-labels, if you just keep feeding all the pseudo-labeled data back in, performance quickly degrades model collapse. Noise accumulates. But if you strategically prune using principles like keeping only the correctly labeled hard examples, when your model generator is strong enough, you maintain stable performance over many iterations of self-improvement.
Okay, so pulling this all together, the big picture is that data curation isn't just some random trick anymore. It's a principled design choice.
Exactly. It's governed by the phase of learning you're in, which is fundamentally determined by your generator quality, rho, relative to the specific task or data slice you care about.
The framework gives you the analytical tools to understand when and why less data can be more effective, bending those traditional scaling laws.
It really reframes how we should think about utilizing large data sets and powerful teacher models efficiently.
The authors naturally point towards next steps too. Where does this research go from here?
Well, the obvious one is moving beyond the linear model assumption, extending this kind of analysis to nonlinear models, perhaps starting with things like the neural tangent, kernel, NTK regime, to see how well these principles translate to deep neural networks.
That seems crucial for direct application to modern AI. What else?
Another big area is making the theory more dynamic. Real systems often use adaptive curation. The model's performance influences the next round of data selection. Think about RLHF or complex self-distillation pipelines. Incorporating those feedback loops into the theory would be really valuable.
Right. The current theory is more of a snapshot, but real training is iterative.
Exactly. And finally, they suggest broadening the evaluation metrics. We've talked a lot about test error or accuracy, but how does theory-guided curation impact things like fairness, robustness, or even the energy consumption and carbon footprint of training?
Yeah, the potential for efficiency gains seems massive, and quantifying that in terms of cost and energy would be huge.
Definitely. It could make training powerful models much more sustainable.
Okay, so this leads us to a final thought, maybe a challenge for everyone listening, especially the engineers building these systems. We now know that the generator quality is the key variable determining whether you should go for keep hard or keep easy more data, low agreement law. But how do you actually measure this effective DRML in a real-world scenario, especially when you're dealing with complex tasks and maybe unlabeled data streams?
That's the million-dollar question, isn't it? If you could get a reliable, real-time estimate of your effective generator quality for the task at hand, you could potentially automate the choice of the optimal curation strategy on the fly. No more guesswork or relying solely on downstream validation metrics. Solving that measurement problem feels like the critical next step to fully unlock the practical power of these theoretical insights.